Okay, this is a lecture where complex numbers come in. Complex numbers have slipped into this course because even a real matrix can have complex eigenvalues. So we met complex numbers there as the eigenvalues and complex eigenvectors. And this is probably the last. We have a lot of other things to do about eigenvalues and eigenvectors. And that will be mostly real. But at one point somewhere we have to see, what do you do when the numbers become complex numbers? What happens when the vectors are complex, when the matrices are complex, what's the inner product of two, the dot product of two complex vectors? We just have to make the change. Just see, what is the change when numbers become complex? Then, can I tell you about the most important example of complex matrices? It comes in the Fourier matrix. So the Fourier matrix, which I'll describe, is a complex matrix. It's certainly the most important complex matrix. It's the matrix that we need in Fourier transform. And the special thing that I want to tell you about is what's called the fast Fourier transform. And everybody refers to it as the FFT. And it's in all computers, and it's being used as we speak in 1,000 places, because it has transformed whole industries to be able to do the Fourier transform fast, which means multiplying. How do I multiply fast? By that matrix, by that n by n matrix. Normally, multiplications by an n by n matrix would normally be n squared multiplications, because I've got n squared entries and none of them is 0. This is a full matrix. And it's a matrix with orthogonal columns. I mean, it's just like the best matrix. And this fast Fourier transform idea reduces this n squared, which was slowing up the calculation of Fourier transforms, down to n log n. N log n, log to the base 2, actually. And it's this, when that possibility hit, it made a big difference. Everybody realized gradually that this simple idea, you'll see it's just a simple matrix factorization, but it changed everything. Okay, so I want to talk about complex vectors and matrices in general, recap a little bit from last time, and the Fourier matrix in particular. Okay, so what's the deal? All right. The main point is, what about lengths? I'm given a vector. I have a vector x. Or let me call it z as a reminder that it's complex for the moment. But later I'll call the components x. They'll be complex numbers. But it's a vector z1, z2, down to zn. So the only novelty is it's not in Rn anymore. It's in complex n-dimensional space. Each of those numbers is a complex number. So this z1 is in Cn, n-dimensional complex space instead of Rn. It's just a different letter there. But now the point about its length is what? The point about its length is that z transpose z is no good. Z transpose z, if I just put down z transpose here, it would be z1, z2 to zn. Doing that multiplication doesn't give me the right thing. Why not? Because the length squared should be positive. And if I multiply, suppose this is like 1 and I. What's the length of the vector with components 1 and I? What if I do this? So n is just 2. I'm in C2, two-dimensional space, complex space, with the vector whose components are 1 and I. All right. So if I took 1 times 1 and I times I and added Z transpose Z would be 0. But I don't, that vector is not, doesn't have length 0, the vector with components 1 and I. This multiplication, what I really want is Z1 conjugate Z1. You remember that Z1 conjugate Z1 is, so you see that first step will be Z1 conjugate Z1, which is the magnitude of Z1 squared, which is what I want. That's like 3 squared or 5 squared. Now if Z1 is I, then I multiplied by minus I gives 1 plus 1. So the component of length, the component I, its modulus squared is plus 1. That's great. So what I want to do then is do that. I want Z1 bar Z1, Z2 bar Z2, Zn bar Zn. And remember that, you remember this complex conjugate. So there's the point. Now I can erase the no good and put is good. Because that now gives the answer 0 for the 0 vector, of course, but it gives a positive length squared for any other vector. So it's the right definition of length. And essentially the message is that we're always going to be taking, when we transpose, we also take complex conjugate. So let's find the length of one. So the vector 1I, that's Z, that's that vector Z. Now I take the conjugate of 1 is 1, the conjugate of I is minus I. I take this vector, I get 1 plus 1, I get 2. So that's a vector, and that's a vector of length square root of 2. Square root of 2 is the length, and not the 0 that we would have got from 1 minus I squared. Okay. So the message really is, whenever we transpose, we also take conjugates. So here's a symbol, one symbol, to do both. So that symbol H, it stands for a guy named Hermite, who didn't actually pronounce the H, but let's pronounce it. So I would call that Z Hermitian Z. Now let me write that word. So his name was Hermite, and then we make it into an adjective, Hermitian. So Z Hermitian Z, ZHZ. Okay. So that's the length squared. Now what's the inner product? Well, it should match. The inner product of two vectors. So inner product is no longer, used to be y transpose x. That's for real vectors. For complex vectors, whenever we transpose, we also take the conjugate. So it's y Hermitian x. Of course, it's not real anymore usually. The inner product will usually be complex number. But if y and x are the same, if they're the same z, then we have ZHZ, we have the length squared, and that's what we want. The inner product of a vector with itself should be its length squared. So this is like forced on us because this is forced on us. So this everybody's picking up what this equals. This is Z1 squared plus Zn squared. That's the length squared. And that's the inner product that we have to go with. So it could be a complex number now. One more change. Well, two more changes. We've got to change the idea of a symmetric matrix. So I'll just recap on symmetric matrices. Symmetric means A transpose equals A, but no good if A is complex. So what do we instead, that applies perfectly to real matrices. But now if my matrices are complex, I want to take the transpose and the conjugate to equal A. So that's the right complex version of symmetry. The symmetry now means when I transpose it, flip across the diagonal, and take conjugate. So for example, here would be an example. On the diagonal, it better be real, because when I flip it, the diagonal is still there, and then when I take the complex conjugate, it has to be still there, so it better be a real number. Let me say 2 and 5. What about entries off the diagonal? If this entry is, say, 3 plus I, then this entry had better be, because I want whatever this, when I transpose, it'll show up here, and I conjugate. So I need 3 minus I there. So there's a matrix that corresponds to symmetry, but it's complex. And those matrices are called Hermitian matrices. Hermitian matrices. A, H equals A. Fine. Okay, and those matrices have real eigenvalues, and they have perpendicular eigenvectors. What does perpendicular mean? Perpendicular means the inner product, so let's go on to perpendicular. Well, when I had perpendicular vectors, for example, they were like Q1, Q2, up to Qn. That's Q is my letter that I use for perpendicular. Actually, I also mean unit length. So those are perpendicular unit vectors. But now so it's a orthonormal basis. I'll still use those words, but how do I compute perpendicular? How do I check perpendicular? This means that the inner product of Qi with Qj, but now I not only transpose, I must conjugate, right? To get 0 if I is not j, and 1 if I is j. So it's a unit vector, meaning unit length, orthogonal. All the angles are right angles, but these are angles in complex n-dimensional space. So it's Q1, Qi bar transpose, or for short, QiH, Qj. So it will still be true. So I'll create a matrix out of those guys. The matrix will have these Q's in its columns, Q2 to Qn. And I want to turn that into matrix language, just like before. What does that mean? That means I want all these inner products. So I take these columns of Q, multiply by their rows. So it used to be Q transpose Q equals I, right? This was an orthogonal matrix. But what's changed? These are now complex vectors. Their inner products involve conjugating the first factor. So it's the conjugate of Q transpose. It's Q bar transpose Q, QH. So can I call this, let me call it QHQ, which is I. So that's our new, you see I'm just translating, and the book on one page gives a little like dictionary. of the right words in the real case, Rn, and the corresponding words in the complex case for the vector space Cn. Of course, Cn is a vector space. The numbers we multiply are now complex numbers. We're just moving into complex n-dimensional space. Okay. Now, actually, I have to say, we changed the word symmetric to Hermitian for those matrices. People also changed this word orthogonal into another word that happens to be unitary as a word that applies, that signals that we might be dealing with a complex matrix here. So what's a unitary matrix? It's just like an orthogonal matrix. It's a square n by n matrix with orthonormal columns, perpendicular columns, unit vectors computed by, and perpendicularity computed by remembering that there's a conjugate as well as a transpose. Okay. So those are the words. Now I'm ready to get into the substance of the lecture, which is the most famous complex matrix, which happens to be one of these guys. It has orthogonal columns. And it's named after Fourier because it comes into the Fourier transform. So it's the matrix that's all around us. Okay. Let me tell you what it is, first of all, in the n by n case. Then often I'll let n be 4 because 4 is a good size to work with. But here's the n by n Fourier matrix. Its first column is the vector of 1s. It's n by n, of course. Its second column is the powers. Actually, better if I move from the math department to EE for this 1/2 hour, and then please let me move back again. Okay. What's the difference between those two departments? It's just math starts counting with 1, and electrical engineers start counting at 0. Actually, they're probably right. So anyway, we'll humor them. So this is really the zeros column. And the first column up to the n minus 1. That's the one inconvenient spot in electrical engineering. All these expressions start at 0, no problem, but they end at n minus 1. Well, that's the difficulty that course 6 has to do. So they're the powers of a number that I'm going to call w. W squared, w cubed, w to the, now what is the w here? What's the power? This was the zeroth power, first power, second power. This will be n minus first power. That's the column. What's the next column? It's the powers of w squared, w to the fourth, w to the sixth, w to the 2, n minus 1. And then more columns and more columns and more columns. And what's the last column? It's the powers of, let's see, actually, if we look along rows, this matrix is symmetric. It's symmetric in the old, not quite perfect way. Not perfect because these numbers are complex. And so it's that first row is all 1s. 1 w squared up to w to the n minus 1. That's the last column is the powers of w to the n minus 1. So this guy matches that. And finally, we get w to something here. I guess we could actually figure out what that something is. What are the entries of this matrix? The ij entry of this matrix. Are you going to allow me to let I go from 0 to n minus 1? So I and j go from 0 to n minus 1. So the 0, 0 entry is a 1. It's just this same w guy to the power I times j. Let's see, I'm jumping into formulas here, and I have to tell you what w is, and then you know everything about this matrix. So w is, well, shall we finish here? What was this? This is the n minus 1 entry. This is w to the n minus 1 squared. Everything's looking like a mess here, because we have, not too bad, because all the entries are powers of w. None of them are 0. This is a full matrix. But w is a very special number. W is the special number whose nth power is 1. In fact, well, actually, there are n numbers like that. One of them is 1, of course. But the w we want is, the angle is 2 pi over n. Is that what I mean? N over 2 pi. No, 2 pi over n. W is e to the I, and the angle is 2 pi over n. Right. Where is this w in the complex plane? It's on the unit circle, right? It's the cosine of 2 pi over n plus I times the sine of 2 pi over n. But actually, forget this. It's never good to work with the real and imaginary parts, the rectangular coordinates, when we're taking powers. To take that to the 10th power, we can't see what we're doing. To take this form to the 10th power, we see immediately what we're doing. It would be e to the I 20 pi over n. So when our matrix is full of powers, so it's this formula. And where is this in the complex plane? Here are the real numbers. Here's the imaginary axis. Here's the unit circle of radius 1. And this number is on the unit circle at this angle, which is 1/n of the full way round. So if I drew, for example, n equals 6, this would be e to the 2 pi over 6. It would be 1/6 of the way round. It would be 60 degrees. And where is w squared? So my w is e to the 2 pi I over 6 in this case, for the 6 by 6 Fourier transform. It's totally constructed out of this number and its powers. So what are its powers? Well, its powers are on the unit circle, right? Because when I square a number, a complex number, I square its absolute value, which gives me 1 again. All the powers are on the unit circle. And the angle gets doubled to 120, so there's w squared, there's w cubed, there's w to the 4th, there's w to the 5th, and there is w to the 6th. As we hoped, w to the 6th coming back to 1. So those are the 6, can I say this on TV? The 6 roots of 1, and it's this one, that primitive one we say, the first one, which is w. Okay. So I said I would probably switch to n equal 4. What's w for that? It's the 4th root of 1. W to the 4th will be 1. W will be e to the 2 pi I over 4 now. What's that? This is e to the I pi over 2. This is 1/4 of the way around the unit circle, and that's exactly I, 1/4 of the way around. And sure enough, the powers are I squared, which is -1, I cubed, which is -I, and finally I to the fourth, which is 1, right? So there's W, W squared, W cubed, W to the fourth. I'm really ready to write down this Fourier matrix for the 4 by 4 case, just so we see that clearly. Let me do it here. F4 is, all right, 1, 1, 1, 1, 1, 1, 1. W, it's I squared, that's minus 1. I cubed is minus I. I could write I squared and I cubed. Why don't I, just so we see the pattern for sure. I squared, I cubed, I squared, I cubed, I fourth, I sixth, I fourth, I sixth, and I ninth. You see the exponents fall in this nice? The exponent is the row number times the column number, always starting at 0. Okay. And now I can put in those numbers if you like. 1, 1, 1, 1, 1, I, minus 1, minus I, 1, minus 1, 1, minus 1, and 1 minus I, minus 1, I. No. Yes. Right. Why do I think that matrix is so remarkable? It's the 4 by 4 matrix that comes into the 4-point Fourier transform. When we want to find the Fourier transform, the 4-point Fourier transform of a vector with 4 components, we want to multiply by this F4, or we want to multiply by F4 inverse. One way we're taking the transform, one way we're taking the inverse transform. Actually, they're so close that it's easy to confuse the two. The inverse of this matrix will be a nice matrix also. So, and that's, of course, what makes it, I guess Fourier knew that. He knew the inverse of this matrix. As you'll see, it just comes from the fact that the columns are orthogonal. From the fact that the columns are orthogonal, we will quickly figure out what is the inverse. What Fourier didn't notice, I think Gauss noticed it, but didn't make a point of it, and then it turned out to be really important, was the fact that this matrix is so special that you can break it up into nice pieces with lots of zeros, factors that have lots of zeros, and multiply by it or by its inverse very, very fast. Okay. But how did it get into this lecture first? Because the columns are orthogonal. Can I just check that the columns of this matrix are orthogonal? So the inner product of that column with that column is 0. The inner product of column 1 with column 3 is 0. How about the inner product of 2 and 4? Can I take the inner product of column 2 with column 4? Or even the inner product of 2 with 3. Let's see, does that, let me do 2 and 4. Okay. What? Oh, I see, yes. Let's see, I believe that those 2 columns are orthogonal. So let me take their inner product and hope to get 0. Okay, now if you hadn't listened to the first half of this lecture, when you took the inner product of that with that, you would have multiplied 1 by 1, I by minus I, and that would have given you 1. Minus 1 by minus 1 would have given you another 1. Minus I by I would have been minus I squared. That's another 1. So do I conclude that the inner product of columns, I said columns 2 and 4, that's because I forgot those are columns 1 and 3. I'm interested in their inner product, and I'm hoping it's 0, but it doesn't look like 0. Nevertheless, it is 0. Those columns are perpendicular. Why? Because the inner product, we conjugate. You remember that one of the vectors in the inner product has to get conjugated. So when I conjugate it, it changes that I to a minus I, changes this to a plus I, changes that second sign and that fourth sign, and I do get 0. So those columns are orthogonal. So columns are orthogonal. They're not quite orthonormal, but I could fix that easily. All those columns have length 2. Length squared is 4, like this. The 4 I had there, this length squared, 1 plus 1 squared, 1 squared, 1 squared, 1 squared is 4. Square root is 2. So if I really wanted them, suppose I really wanted to fix life up perfectly, I could divide by 2, and now I have columns that are actually orthonormal. So what? So I can invert right away, right? Orthonormal columns means, now I'm keeping this 1/2 in here for the moment, means F4 Hermitian, can I use that? Conjugate transpose times F4 is I. So I see what the inverse is. The inverse of F4 is, it's just like an orthogonal matrix. The inverse is the transpose. Here the inverse is the conjugate transpose. So fine. That tells me that anything good that I learn about F4, I'll know a similar fact about its inverse, because its inverse is just its conjugate transpose. Okay, now, so what's good? Well, first, the columns are orthogonal. That's a key fact then. That's the thing that makes the inverse easy. But what property is it that leads to the fast Fourier transform? So now I'm going to talk in these last minutes about the fast Fourier transform. Here's the idea. F6, our 6 by 6 matrix, there's a neat connection to F3, half as big. There's a connection of F8 to F4. There's a connection of F64 to F32. Shall I write down what that connection is? What's the connection of F64 to F32? So F64 is a 64 by 64 matrix whose W is the 64th root of 1. So it's 1/64th of the way around in F64. And F32 is a 32 by 32 matrix. Remember, they're different sizes. And the W in that 32 by 32 matrix is the 32nd root of 1, which is twice as far. See that key point. That's how 32 and 64 are connected in the W's. The W for 64 is 1/64th of the way. So all I'm saying is that if I square the W64, that's what I'm using for the 1 over W60. This is Wn is e to the I 2 pi over n. So W64 is 1/64th of the way around it. When I square that, what do I get but W32? Right? If I square this matrix, I double the angle. If I square this number, I double the angle. I get the W32. So somehow there's a little hope here to connect F64 with F32. And here's the connection. Okay. Let me go back. I'll do it here. Here's the connection. F64, the 64 by 64 Fourier matrix, is connected to two copies of F32. Let me leave a little space for the connection. So this is 64 by 64. Here's a matrix of that same size because it's got two copies of F32 and two zero matrices. Those zero matrices are the key, because when I multiply by this matrix, just as it is, regular multiplication, I would need 64. I would have 64 squared little multiplications to do. But this matrix is half zero. Well, of course, the two aren't equal. I'm going to put an equal sign, but there has to be some fix-up factors, one there and one there, to make it true. The beauty is that these fix-up factors will be really almost all zeros. So that as soon as we get this formula right, we've got a great idea for how to get from the 64 squared calculations. So this originally we have 64 squared calculations from there, but this one will give us, we don't need that many. We only need 2 times 32 squared, because we've got that twice, and plus the fix-up. So I have to tell you what's in this fix-up matrix. The one on the right is actually a permutation matrix, a very simple odds and evens permutation matrix. The ones show up. I haven't put enough ones. I really need 32 of these guys, a double space, and then you see it's a permutation matrix. What it does, shall I call it P for permutation matrix? So what that P does, when it multiplies a vector, it takes the even numbered components first, and then the odds. You see this one skipping every time is going to pick out x0, x2, x4, x6, and then below that it will pick out x1, x3, x5. And of course, that can be hardwired in the computer to be instantaneous. So that says, so far, what have we said? We're saying that the 64 by 64 Fourier matrix is really separate your vector into the even components and the odd components, then do a 32 size Fourier transform onto those separately, and then put the pieces together again. So the pieces, putting them together, turns out to be I and a diagonal matrix, and I and a minus that same diagonal matrix. So the fix-up cost is really the cost of multiplying by D, this diagonal matrix, because there's essentially no cost in the I part or in the permutation part. So really, it's the fix-up cost is essentially, because D is diagonal, is 32 multiplications. There you're seeing, of course, we didn't check the formula, or we didn't even say what D is yet, but I will. This diagonal matrix D is powers of W. 1 W squared down to W to the 31st. So you see that to do a multiplication by D, I need to do 32 multiplications. There they are. Then, but the more serious work is to do the F32 twice separately on the even numbered and odd numbered components. So twice 32 squared. So 64 squared is gone now. And that's the new count. Okay, great. But what next? So we now have the key idea. we would have to check the algebra, but it's just checking a lot of sums that come out correctly. This is the right way to see the fast Fourier transform, or one right way to see it. Then you've got to see what's the next idea. The next idea is to break the 32s down. Break those 32s down. So we have this factor, and now we have the F32, but that breaks into some guy here, F30, F6, F16, F16. Each F32 is breaking into 2 copies of F16. And then we have a permutation, and then so this is this was a 64 size permutation, this is a 32 size permutation. I guess I've got it twice, because I'm just using the same idea recursively. Recursion is the key word. That on each of those F32, so here's 0, 0. It's just to get F32, this is the odd-even permutations. So you see the combination of those permutations, what's it doing? This guy separates into odds and into evens and odds. And then this guy separates the evens into the numbers that the even evens, which means 0, 4, 8, 16. And even odds, which means 2, 6, 10, 14. And then odd evens and odd odds. You see, together these permutations then break our vector down into x, even, and 3 other pieces. Those are the 4 pieces that separately get multiplied by F16, separately fixed up by these i's and d's and i's and minus d's. So this count is now reduced. This count is now, what's it reduced to? So that's going to be gone. Because 32 squared, that's the change I'm making, right? The 32 squared, so it's this that's now reduced. So I still have 2 times it, but now what's 32 squared? It's gone in favor of 2 16 squareds plus 16. That was, and then the original 32 to fixed. Maybe you see what's happening even easier than this formula is. When I do the recursion more and more times, I get simpler and simpler factors in the middle. Eventually, I'll be down to 2-point or 1-point Fourier transforms. But I get more and more factors piling up on the right and left. On the right, I'm just getting permutation matrices. On the left, I'm getting these guys, these i's and d's. So that there was a 32 there, and each one of these is costing 32. Each one of those is costing 32. And how many will there be? See the 32 for this original fix-up, because D had 32 numbers. 32 for this next fix-up, because D is 16 and 16 more. I keep going. So the count in the middle goes down to zip, but these fix-up counts are all that I'm left with. And how many factors, how many fix-ups have I got? Log n. From 64, 1 step to 32, 1 step to 16, 1 step to 8, 4, 2, and 1. 6 steps. So I have 6 fix-up factors. Finally, I get to 6 times the 32. That's my final count. Instead of 64 squared, this is log to the base 2 of 64 times 64. Actually, half of 64. So actually, the final count is n log to the base 2 of n. That's the 32, a half. So can I put a box around that wonderful, extremely important and satisfying conclusion that the fast Fourier transform multiplies by an n by n matrix, but it does it not in n squared steps, but in 1/2 n log n steps. And if we just complete by doing a count, let's suppose a typical case would be 2 to the 10th. Now, n squared is bigger than 1,000,000. So it's 1,024 times 1,024. But what is n? What is 1/2? What is the new count done the right way? It's n, the 1,024, times 1/2, and what's the logarithm? It's 10. So times 10 over 2. So it's 5 times 1,024, where this one was 1,024 times 1,024. We've reduced the calculation by a factor of 200 just by factoring the matrix properly. This was 1,000 times n. We're now down to 5 times n. So we can do 200 Fourier transforms, where before we could do 1. And in real scientific calculations where Fourier transforms are happening all the time, we're saving a factor of 200 in one of the major steps of modern scientific computing. So that's the idea of the fast Fourier transform, and you see the whole thing hinged on being a special matrix with orthonormal columns. Okay, that's actually it for complex numbers. I'm back next time really to real numbers, eigenvalues and eigenvectors, and the key idea of positive definite matrices is going to show up. What's a positive definite matrix? And it's terrific that this course is going to reach positive definiteness, because those are the matrices that you see the most in applications. Okay, see you next time. Thanks.